John is a co-founder and technical fellow of Doulos. John spent many years working in EDA, specializing in hardware description and verification languages and mythology, and is well regarded in the industry for his contributions to language standards. Recently, he's focused on machine learning and neural networks. John still creates and delivers training courses, webinars and seminars worldwide. Thank you, John.
So, hi everybody, welcome. So I'm going to talk today for about half an hour on deep learning for verification engineers. I love talking about deep learning. Deep learning is just such an extraordinary subject, so extraordinary in its scope. And the whole story of deep learning is just an amazing one, which really begs the question of how useful it's going to be for verification engineers. And to be honest, I'm probably going to spend more today talking about deep learning than I am talking about verification as such, and I'll explain why as I go through this presentation. So I'm going to give a very brief introduction to machine learning and deep learning, dive a little bit into what deep learning is and how it works, and just enough, I hope, to give you some sort of flavor as to how significant it's likely to be for you as verification engineers and how you might end up using deep learning as verification engineers. So I guess I should say at the outset that there's a number of different ways in which deep learning is going to be relevant to all of us. I mean, one way is going to be as consumers of deep learning and machine learning in our everyday lives, consuming devices and algorithms. Also, as verification engineers, we're going to be verifying systems that will be increasingly implementing deep learning algorithms. So at some point, many of us are going to have to verify devices or be verifying systems that include deep learning as some part of the functioning of the system. And then maybe the topic that you're most interested in is how is deep learning going to impact the algorithms and the tools that you use in verification. So I'll certainly address that topic, but I'm not going to give you a whole lot of very detailed information. Of course, I would claim it doesn't exist yet. I'll say more about that when we get there. Anyway, back to the beginning of the story, introduction to machine learning and deep learning. So deep learning is most definitely a subset of machine learning, and machine learning is a subset of the broader field of artificial intelligence. And the term AI gets used a lot in marketing presentations these days. Like I saw AI was used as the topic of this DVClub meeting because it kind of sounds cool to talk about AI. AI is a very broad topic going right back to the 1960s and earlier. In its early incarnations of AI, it was all about databases of knowledge, logical inference, expert systems. So AI is still alive and well as a very broad field. Machine learning is one specific part of that very broad field, which is giving computers the ability to learn without being explicitly programmed. Machine learning is a bunch of mathematical algorithms whereby computers can learn stuff without being programmed. And deep learning is a particular subset of machine learning, and the term deep learning is used where the particular machine learning algorithm concerned is a neural network with many hidden layers. And I hope I'll say just enough about that in the next half hour to whet your appetite and give you some intuition as to what's going on. So there are many machine learning algorithms that these days sometimes get referred to as classical machine learning algorithms to distinguish them from deep learning. So classical machine learning algorithms can perform a range of tasks: classification, regression, dimensionality reduction, clustering data, anomaly detection. I remember using some of these algorithms as an intern over 40 years ago. I was literally using regression algorithms over 40 years ago that have a distinct family resemblance to the very latest deep learning algorithms. But there's a whole bunch of machine learning algorithms as well: support vector machines, Markov models, decision trees, random forests, reinforcement learning, genetic algorithms, and somewhere down in this list, neural networks. So the first big takeaway from this whole presentation of mine is that neural networks and deep learning are just one part of a broad range of machine learning algorithms. And many of these machine learning algorithms seem to have had a new lease of life now that deep learning has become such a hot topic. There's a renewed interest in classical machine learning algorithms just because deep learning has given this subject so much momentum. So deep learning in particular is machine learning using a deep neural network. In effect, deep learning involves some very, very simple mathematical algorithms that get applied very intensively with a huge amount of computation to very, very big data sets. And deep learning is often applied end to end. I'll say more about that in a minute, but it essentially means that you present your mathematical algorithms with a bunch of inputs, a bunch of outputs, and you get the algorithms to figure out all the internal structure for themselves. So deep learning algorithms don't require a lot of domain-specific knowledge. Deep learning algorithms in the field of computer vision have actually replaced a lot of domain-specific knowledge. There is a story that many computer vision experts are now redundant because their life's work has been supplanted by a few deep learning algorithms. So the whole deep learning story has really been fueled by the ImageNet challenge. The ImageNet challenge was an academic challenge that's been in place many, many years, which is a challenge to academics to develop computer vision algorithms to recognize images belonging to the ImageNet dataset. So the ImageNet dataset consists of 1.2 million images that fall into 1,000 categories, and there's a challenge to try and write computer algorithms to sort out these images and identify them. And deep learning really became hot in 2012, only 7 years ago. And in 2012, suddenly a convolutional neural network, won the ImageNet challenge for the first time with a top 5 error rate of 16.4%, which was a dramatic improvement on the previous year's winner, which wasn't a neural network. So 2012 marked a huge change in the fate and the fortune of neural networks. Prior to 2012, neural networks had been through the dark ages for many, many years. I remember playing with neural networks back in the 1980s and 1990s when they looked really promising, really hopeful, really interesting, but you couldn't actually do anything very useful with them. And it turns out the reason you couldn't do anything very useful with them is the computers simply weren't fast enough and didn't have enough capacity. There was a story back in the 1990s, I think it was, that a particular researcher figured out that their neural network research was going nowhere because the network that they were using just didn't work very well. More recently, the same guy reran that network, allegedly, over the last few years, and discovered that actually it would have worked, there was just a bug in the network. And the reason that the bug wasn't found is that computers weren't fast enough, essentially. So in 2012, for the first time, there was enough computing power around for neural networks to really show how good they are. And since 2012, each year between 2012 and 2016 showed a significant improvement in the performance of neural networks. In fact, they were getting so good year by year that people wondered how well humans would do at the same task. So around and about 2014, a human being was given the unenviable task of having a go at the ImageNet challenge themselves in place of an algorithm. And they came up with an error rate of about 5%. So the challenge was then on to beat the human error rate of 5%, and that happened in the next year. And now we've still got an error rate on this challenge of just about 3%. We still keep seeing improvements every year, but it's pretty much peaked at 3%. So this is a remarkable story, really. Neural networks suddenly proved to be very, very good at processing images, and they also proved to be very, very good at all sorts of other tasks. And all of this came about because of faster computers and bigger data sets. So since 2012, we've seen neural networks often outperforming previous state-of-the-art algorithms in all sorts of different problem domains. And we've also seen neural networks solving whole new classes of problem. And if you're not aware of just how hot and interesting this field is, just go Google something like exciting applications of neural networks, and you'll find lots of websites dedicated to mind-boggling applications of neural networks. This technology is just extraordinary. And because it's so extraordinary, you can probably even hear how excited I am about it, it gets overhyped. Of course it gets overhyped. And so right now it's kind of difficult to sort out the hype from the truth in this whole field because, of course, it's all getting overhyped. In a sense, however, it's still very, very early days. And while I'm sure that there's a certain amount of overhyping going on, it's also very difficult to understate just how significant neural networks could be. To date, only a tiny fraction of the academic work has really made it out into the wild. There's an enormous momentum of research going on now in neural networks. And the sky's the limit right now. Nobody knows where this could end. Nobody knows what amazing advances are coming up in the next few years. So if you haven't cottoned on to what's going on yet in the neural network world, it's kind of time to wake up to it, because the world is changing very rapidly. And even if some of the hype just doesn't turn into reality, there's still an enormous amount of progress being made in this field. So here's just some of the low-hanging fruit that you will be using already. Recommendation engines on websites, fraud detection on financial transactions, natural language transaction for written language and spoken language. Then there's a whole bunch of really cool applications for embedded systems that you might end up verifying, such as image recognition, object detection, image segmentation, speech recognition, keyword spotting, anomaly detection and industrial controls, detecting when motors or other industrial equipment are about to fail. So these are just a few of the applications of neural networks that have made it out into the wild. There are many more applications and many, many more lines of research waiting in the wings, and really anything could happen. So the algorithms that I'm talking about today really split into two parts: unsupervised learning and supervised learning. Most of which, what I'm going to talk about today, is supervised learning, but unsupervised learning algorithms have their place as well. With an unsupervised learning algorithm, what you do is present the learning algorithm with a bunch of data and tell the learning algorithm, go learn something about this data, go find some structure in the data. So unsupervised learning algorithms are inherently very challenging because they're so open-ended. An unsupervised learning algorithm is just told to go off and learn something. Now, these algorithms would typically do things like partitioning data into clusters based on similarity of the data in some sense, or finding hidden patterns in data that aren't obvious, or maybe picking out anomalous data samples. So an example, a possible example of unsupervised learning in the functional verification space would be spotting anomalous simulation runs. So maybe as the data set, you could use a whole bunch of statistical data from verification runs, you know, the amount of CPU time, the memory usage, the disk usage, the temperature of the CPU, any other data that you can collect on verification runs, and then used unsupervised learning algorithms to spot anomalous data cases. So anomalous cases might actually be highlighting verification runs that deserve further investigation. Maybe they use an unusual amount of runtime or an unusual amount of disk. And there's definitely work going on like this right now. So a presentation was given at DVClub in San Jose in February this year, using exactly this kind of topic. I don't think they were actually even using an unsupervised learning algorithm. I think they were simply using regular statistics to look for statistical anomalies in a whole bunch of verification runs to try to look for potential issues. Deep learning, however, is an example of supervised learning. So let's take a slightly deeper dive into supervised learning to figure out what that's about. So with supervised learning, what we're trying to do is to learn to predict the output given the input. So you feed a supervised learning algorithm, such as a neural network, with a bunch of input data, a bunch of output data, and you try and train your model or network to predict the output from the input. And the example that I like to use here will be the example of autonomous driving, where for the input to our model, we would actually take images going into a video camera. So fix a video camera to the front of your car if it hasn't got one already, then drive around for a few million miles and actually record the steering wheel movements that occur as a result of the images coming into a video camera. It would be entirely practical to set this up as a deep learning problem. How well it would work is a different matter, but you could certainly set it up. So literally the input would be a stream of video images coming in from a camera, and the output would be the position of the steering wheel. Then we'd drive our car around during a training phase and try to predict the relationship between what the car can see, what the camera can see off the road, and the movements of the steering wheel. That's what I mean by an end-to-end problem. We're giving our learning algorithms the task of just predicting the input from the output without saying anything about computer vision, anything about how vision systems are supposed to work, anything about control systems for cars, anything about how a car's engine and transmission works. We're just saying predict the steering wheel movements from the input data. That's what I mean by an end-to-end problem. And that's what deep neural networks are capable of doing. So for supervised learning, such as deep learning, we start off with a training phase where we're training a neural network to solve a problem like that. And training is typically performed these days on many big GPUs. So you'd typically be using a farm of large GPUs and train them for many weeks to build a model for a problem like this. Then comes the deployment phase, where you would deploy a trained model out in the field. And when the model is out in the field, you then present the model with novel input, and it would try to predict the output. So in this case, you would feed the model with the video images coming into your car, and it would predict how the steering wheel needed to move, or maybe actually move the steering wheel in the case of an autonomous vehicle. And this stage is termed inference. The term inference is universally used for what happens when you deploy a neural network in the field and it does its stuff. Personally, I don't like this term inference because it's not doing inference in any sense that I understand it. This is not logical inference or mathematical inference. It's just a neural network doing its thing when you deploy it and feed novel input into that network. So inference can be performed across a whole range of different execution engines, different processors, from very low-end microcontrollers, application processors, CPUs, GPUs, FPGAs, SoCs, custom neural network processors, neuromorphic chips that model biological neurons. Everything's going on, and there's a massive amount of research going on right now in this space. So in the particular case of a neural network, what you do is to take your training data, feed it into a neural network that will try to make some kind of prediction of the results. In this case, what we're trying to do is to predict the breed of cat. So our training data in this case might be cat images, and the prediction is trying to predict the breed of cat. And what we would do in such a case is to compare the prediction with the so-called ground truth using a cost function. So in neural network jargon, the ground truth is the truth, the labels on the training data, in this case the particular breed of cat. The network makes a prediction, and the cost function then compares the prediction with the ground truth. So we start off with an untrained neural network. We're going to have a really poor prediction, and the error will be very large, the cost will be very high. A neural network is actually composed of multiple layers. Each of these layers is composed of individual units and neurons, and each of these units and neurons perform very, very simple mathematical functions, typically multiplies and adds. So each of the arrows in this diagram has got a weight associated with it. We're multiplying the value of the previous unit by a weight, adding those values together to create the input to the next unit. So neural networks, in case you didn't know already, essentially perform very, very simple mathematical functions and do it repeatedly with no domain-specific knowledge. So if you can apply a neural network to the solution of a new problem, you don't really need to know anything about how that problem's been solved before. You simply throw raw data, raw input data, raw output data at your neural network and get it to learn the relationship between the input data and the output data. Deep diving a little bit more, the hidden neurons, the hidden units in such a network actually consist of two parts. There's a linear function that's simply doing a weighted sum of its inputs, and then a non-linear activation function. And there's a variety of non-linear activation functions in common use today. Go back a few years and the typical non-linear activation function would have been a logistic or a sigmoid function. Today, the logistic or sigmoid function in many networks has been replaced by the so-called ReLU function, or rectified linear unit, which is just a straight line in a kink with a kink in it. Why is the straight line with a kink in it used rather than an S-shaped curved? Well, the practical answer is it seems to work better. Networks using ReLUs seem to train faster than networks using sigmoid functions. And today, deep learning is very much an experimental science. The justification for many of the architectural decisions in neural networks today is try it and see. It just seems to work better. This is still a very, very young field that's changing all the time. Lots and lots of innovations going on, literally every week. Extremely dynamic field. So once again, you've got to be very careful at judging what you're seeing in industry right now, because it's only representative of a tiny fraction of the research, as I've said before. So a deep neural network is just one of these engines doing lots and lots of multiplies and additions with more than one hidden layer. That's how it qualifies for the term deep, and some nonlinear activation functions. And at the output, we're comparing the predicted output of the network with the so-called ground truth, and then jiggling all the weights and biases inside the network in order to try to minimize the value of the cost function. So the cost function you can visualize as some kind of landscape with lots of humps and bumps on it. The X and Y axes here are just two of the trainable parameters. So each of the weights and biases here represents a trainable parameter of our network. This particular cost function is showing just 2 dimensions. In practice, there'd be as many dimensions as there are trainable parameters, which is going to mean millions of dimensions. So this cost function would actually be a function of a space containing millions of dimensions. Nonetheless, what we're trying to do as we train this network is to simply go downhill on this cost landscape. So training a neural network means going downhill on the cost landscape, trying to find a low point on the cost landscape. And that's actually done by a bunch of algorithms known as gradient descent algorithms, essentially trying to go downhill on this cost landscape. So at each step here, as we're going downhill on the cost landscape, we're adjusting the values of all of the weights in our network, all of our trainable parameters, by incrementally changing the values of those parameters in order to move us downhill to a lower value in our cost function. And really, essentially, that's what training a neural network is. It's trying to incrementally jiggle all the trainable parameters in the network so that we can gradually move downhill. And the extraordinary thing about this very, very simple algorithm is it works amazingly well. Mathematicians are still trying to figure out exactly how this works. It's really early days in terms of the mathematics. There's a few early results, but really most of the work is still to be done in terms of the mathematical underpinning of all of this stuff. And come to think of it, most of the engineering work is still to be done. It really is early days, and yet it's been amazingly successful already. So here we're looking at artificial neural networks, which are inspired by the biological neural network in your brain, but definitely different from biological neural networks. And the kind of artificial neural networks that have made it out into the wild so far are mostly convolutional neural networks. They're good at image processing. Regional convolutional neural networks, they're good at object detection. And object detection means working out where an object is in an image. And also recurrent neural networks with loops in, and they're good where you've got variable length input and output sequences, such as natural language processing. So if you come across a neural network that's translating one language into another language, that's probably a recurrent neural network. So typical neural networks for image recognition these days would be something like the Inception network, which was one of the very well-known ImageNet winners. The Inception network has got of the order of 100 layers and something like 24 million trainable parameters, depending exactly which network you're talking about. So tens of millions of trainable parameters, weights and biases in this network. And that would really be appropriate for deploying on the cloud if you're doing inference in the cloud. If you're doing inference on a mobile device or at the edge, then there are other networks that are specialized for edge computing and mobile devices, such as MobileNet, for example. So MobileNet version 2 comes in various flavors, various widths and depths, but even that has somewhere between 1.6 million and 6 million parameters. So you may ask, how much data does it take to train a network with 6 million parameters? And the rule of thumb is that it takes something like 2 data samples per parameter. So in other words, if you've got a network of 6 million parameters, you're going to need something like 12 million data samples to train this network. And if you're really listening to what I'm saying and wide awake, you might have remembered I said that the ImageNet dataset only has 1.2 million parameters. So how do you train a network with 24 million parameters on a dataset with something like 1 million parameters? And the answer to that one is image augmentation. In other words, you use computer algorithms to synthesize additional images to add them to the data set. And in the case of images, that can be done in a quite straightforward way by distorting the images, stretching them, shrinking them, changing their aspect ratios, changing their colors and so on, in order to generate the amount of data that you need. But the big point here is that you need a lot of data to do this deep learning stuff. So neural networks really came to the fore. The renaissance of the neural network came about because of the availability of computing power, and neural networks really exploit that computing power. So to do deep learning, you need huge data sets. And one of the commonest stories these days as people try to deploy machine learning and deep learning is the discovery that very often you simply don't have a large enough data set to warrant the use of deep learning algorithms. So there are many cases these days, I'm sure including cases in the verification space, where researchers start off thinking they're going to try applying deep learning to a verification problem and soon discover that they simply don't have enough data, but it may very well be that you could apply a machine learning algorithm successfully. So let's take a look at machine learning and deep learning in EDA and verification. And perhaps the application that's most farthest along is not in the verification space at all, it's in the physical design space. So companies like Solido, for example, who Mental Graphics bought, they're using machine learning and deep learning in the physical design space to actually make predictions about mask sets. And that's an area where you do have huge amounts of data, and deep learning could certainly apply. So you might be able to take mask set data, massive amounts of mask set data, and use it to predict properties of the behavior of a design, like yield or timing or something like that from a mask set. So that would be a very, very practical and tractable application of deep learning in the EDA space. Another practical application coming closer to home might be predicting the delay or latency or power through an IP block. So maybe the input are the parameters of a parameterized hardware IP block, the output is the delay through the block, and it would be perfectly practical to couch that as a machine learning problem. Another practical problem would be informal verification, where you're trying to optimize the performance of the formal verification engine. And in fact, tools like this have been released, and some of the big formal tool vendors are releasing tools exactly like this, set up as a machine learning problem. So the machine learning is looking at the choice of formal verification engine. The output is the proof time to convergence. And then we're using machine learning in order to optimize the deployment of formal verification engines in order to optimize the proof convergence time. Getting more ambitious, and this is more of a research topic, you might try and do something like predict the location of bugs in constrained random verification, or maybe predict what your final coverage is going to be in the case of constrained random verification. So the input data for the learning problem in this case might be all of your simulation logs, fault reports, coverage results, and you might be using all of that information to try to predict where to look for the bugs, or what the final coverage might be given the way things are going. And you could certainly set this up as a machine learning or a deep learning problem. And indeed, there have been papers published at verification conferences for the last few years on this topic. There was some at DVCon this year. But it's really an open question, I would suggest, on how well it's really going to work. Finally, if you're getting really ambitious, how about the input to our deep neural network is the specification for a bunch of RTL blocks. So you input the RTL code, and the output is a test bench to verify those blocks. Well, there is research work being done. There was a couple of papers at DVCon San Jose this year trying to do it, or try to move toward exactly this, but I really don't think it's going to happen in the short term. So you could try to set this up, and researchers are working in this kind of area, but it's probably too ambitious for the first time, for the short term. Anyway, I'm coming to the end, I'm out of time, so if you want to know more about deep learning for engineers, then pop along to Verification Features on June the 12th, when we'll be giving what's really an extended version of this tutorial, an extended tutorial on deep learning for engineers. And if you really want to know more, then of course at Doulos we'll be happy to sell you a training class. So we offer a 5-day training class on practical deep learning. Do contact us at Doulos if you want to know more on that subject. So with that, I'll hand back to you, Sarah.
Thank you, John. I appreciate that. We're just going to... Mike, we should be able to hear you now. Can we check your audio, please?
Yeah, can you hear me okay?
Yes, we can. That's a great relief for me.
So just first of all, a big thank you to John. I know we're short of time now, Sarah. Do you have time for questions or not?
Yes, we do. Are there any questions from Bristol? No, there's one question from the online.
Okay.
And that is there any tool that can be recommended to start experimentation?
Sure. So just go onto the web and Google, and there's all sorts of stuff. I mean, one tool that you can start using very easily is the Google Colabs tool. And Google actually provides you with an online tool where you can just go into a web browser, start typing and using deep learning, courtesy of Google. But really, it's There's an enormous amount of information on the web. It's being added to all the time. So just go Google it. You'll find videos, tutorials, free stuff, paid for stuff, software that you can access online, examples you can access online. The whole thing is just exploding.
Lovely, thank you. We'll quickly go to Cambridge. Bear with me just a second. Cambridge, do you have any questions for John? Bear with me just a second, sorry. Apologies, Cambridge, do you have any questions for John?
No questions from Cambridge.
Thank you. Lovely. That's all for quick questions, Mike.
Okay, just to add to John's answer as well, I've been using MATLAB for my machine learning algorithms. So if you've got access to MATLAB as well, you can learn it there. Just a clarification as well, John mentioned about verification futures. There's tutorials on the Wednesday afternoon, but the full conference is on the Thursday, the following day on the Thursday. That's the full conference. There is going to be a track on using AI in verification and testing. So John's given us a good introduction, but on the day itself, on verification futures, the full day, there's a track on the application of AI to verification and software testing. And the day before, as John mentioned, on the Wednesday afternoon, John's going to give them a longer class on deep learning. If you're interested in that, you'll be sent all the links. Okay, thanks, Sarah.
Lovely, thank you.